Here is the data pertaining to AdaBoost. Let me do the movie classification. Same thing, head, top 5, info, how many rows, how many columns, how many float, how many integers, how many numbers, same thing. Then if you feel that 3D and genre are something which have to be converted into dummy variables, do so. Then you look at the head if you want to segregate the inputs and segregate the output. Then split the data into training and test. Then here we are importing AdaBoost. And in AdaBoost, we are saying I want to run 5,000 algorithms, and you know the learning rate concept here. So you're now fitting the model on training and test. Since it's 5,000 decision tree algorithms, it would take certainly some time. But all of those are decision tree algorithms in AdaBoost are decision stumps. Decision stump means decision tree with one split. Then you get into accuracy. You predict, you come up with a confusion matrix. You calculate the accuracy at 62. When you look at the accuracy on training data, it is 88. Is it overfitting? Sure. This is overfitting. So you need to once again go to your hyperparameters, take all the hyperparameters, experiment them. How do you experiment? Using grid search algorithms. Then let's go to gradient boosting. This is also pretty straightforward. Once again, we have the same data set, movies classification data set. The same logic applies. Load the data, read it, head, info, do the dummy variable creation, input and output, split them, and then partition the data. Until here, it's the same. Only thing is we are importing gradient boosting classifier. We are taking all the default hyperparameters and you're fitting your model. Once you fit your model, you take accuracy and confusion matrix. You say a confusion matrix of actual values and predicted values. So you're saying take this model that you built, predict on the test data, and you get predicted values. Compare the predicted values and actual values to look at the confusion matrix. Look at the accuracy, it's only 0.57. When you use the default hyperparameters here, you didn't give any hyperparameters. Here, if I change the hyperparameters, what will happen? Let's see. Then when you save all the hyperparameters in this, when you say fit, you're fitting the model on training and training data. Then you're importing accuracy score and confusion matrix. You can get the confusion matrix out. Overall accuracy. Is it overfitting? Yep, sure. 0.88 and 0.61. Once again, try out various hyperparameters, figure out what set of hyperparameters will help you provide a right fit model. Then we have extreme gradient boosting. Again, the same data set you loaded, get the dummy variables, get the input and output data, split it. Then from here onwards, it'll be different. You import XGBoost as XGB. And from that, you are importing classifier and you're giving the hyperparameters, maximum depth, number of estimators, learning rate, number of jobs equal to minus. Let me keep this window open. And remind me about Gini indexes just in case I forget, because it will hardly take 2 minutes. Okay. Now if I say dot fit, Okay, done. How many algorithms did it run? 10,000 algorithms with depth equal to 5. So just like that, it completed. Right. Now you take the accuracy score and confusion matrix. Look at your confusion matrix. Look at your accuracy. It's 0.66 something. You also have something called as an importance plot, which will tell you what are the variables which are very important. More the score, more is the importance. You probably want to, if I were you, I would probably throw away everything from 350 onwards. Okay. From here onwards, I would probably do away with everything. I'll use only those features which have very good information. And I'll proceed. Okay. Then you can try it with different other hyperparameters. I am trying out with all these set of hyperparameters. Gamma, column, sample, byte tree, subsample, alpha, maximum depth, all these different options I want to try out. So we go to grid search cross validation. We are saying take XGBoost classifier. Then when it comes to parameters to experiment, use these parameters. Number of jobs equal to -1 means use all the processors, use 5-fold cross validation. Scoring mechanism is accuracy. %. But when it comes to your CPU, entire 100% of CPU is being utilized. So if you have high processor or multiple processors, then I think it will show you the true results. Anyways, it is okay. Some warning messages. Warning messages, I think, can be safely ignored. Let me run it. So these are the best hyperparameters and the best algorithm you're saving in this. Once you save the best algorithm, what would you do? You would use that best algorithm and you predict on your test data. This would give you the predicted values. Compare it with the actual values. And then ultimately you get your accuracy. Okay, you can also test on your test training data. It's giving 100%. So certainly it is overfitting. So again, you need to play around with your hyperparameters. Okay, fine. One small concept on Gini index and we'll be done. We have discussed about information content and we discussed about expected information content. This expected information content is called as entropy, which is a measure of impurity. Nothing but error. If you say 1 minus entropy, you get measure of purity, which will give you accuracy. Then we have something called as Gini index. Gini index is a measure of purity. And when I say 1 minus Gini index, this will give you measure of impurity. Okay. So one is going with the hard assignment. Hard assignment means you only take the majority class. Out of these two classes, you have 60 red and 5 green. So majority is 60. So you assign it red class. The output, whatever is a new observation, you assign it a red class. Whereas here you have 10 and 60, which is a dominant class, 60 green. So you assign a green class. This is hard assignment. But your Gini index will look at soft assignment. Gini index says that not just the dominant class, but the other class also should be considered. Why? We calculating the probabilities. So how will it calculate? What is the formula for expected value? Xi into probability of Xi. Here you have a two class problem. So you write the summation of I equal to 1 until 2, Xi into probability of Xi. Then I equal to 1 means X1 into probability of X1, summation, so plus I equal to 2 means you would have X2 into probability of X2. Okay. X1 is what is the proportion of, say, for example, what is the proportion of 5? How many do you have? What is the proportion of 5 in 65? What is the proportion of 10 in 100? 10 by 100, which is 10%. Correct? What is the proportion of 5 in 65? 5 by 65. That's the proportion. Into, do you know what here? Probability value also happens to be the same. If I say it rained 1 out of 10 days, what is the probability that it's going to rain today? 1 by 10. 5 out of 65 are green. So what is the probability that the new entry will be green? 5 by 65 plus. You also, now you consider the non-dominant class. You also now take the dominant class, 60. So how many red do you have out of 65? 60 by 65. That's the proportion into what is the probability that the next class will be red class? 60 by 65. This way of calculating the probability would give rise to a value which is called as Gini index, which is measure of purity. Entropy is measure of impurity. Classic interview question. What is the difference between entropy and Gini index? Entropy is a measure of impurity. Gini index is measure of purity. Yeah. So here the best estimator is nothing but your classifier, which is using all these hyperparameters. That is called as your best estimator. Best estimator. Okay, is this. Best set of parameters are these. So what does that mean? You are using this estimator with these set of hyperparameters, which is giving you the best result. Making sense, Rushali? Okay, one of our friend had to stop. Okay. Now, for every algorithm that you learn, you need to be aware of, at a high level, how is that algorithm operating? And second thing, what are the hyperparameters? Out of those hyperparameters, what are the hyperparameters which can be used as regularization techniques? Regularization techniques will help you avoid overfitting by maintaining bias variance trade-off. When we have run KNN algorithm, how was KNN algorithm working based on distance? This high level information you need to have. It has only one hyperparameter, which is K value, which also happens to be a regularization technique. When it comes to decision tree, how was the algorithm working at a high level? By calculating entropy. That is, entropy is nothing but loss, error. And then it was giving you rules, different classification rules. What were the hyperparameters? There were many hyperparameters which fall under pruning techniques. Within pruning, you have pre-pruning and post-pruning. So what are the techniques that you have within this and this? You take those and all those would be part of your regularization techniques. Then we have random forest. Random forest is nothing but collection of multiple decision trees. So whatever logic gets applied here, here also the same logic gets applied. But one additional thing is square root of p and p by 3. If you have regression based algorithms, then at each split, it will choose p by 3. Here at each split for classification, it uses square root of p. Okay. Then you should be aware of all the various hyperparameters and which of those happen to be your regularization techniques. Same is the case with bagging. Same is the case with stacking. Same is the case with boosting. For every algorithm at a high level, you need to understand how that operates. What are the hyperparameters? Which of those happen to be a regularization techniques? Okay. Yes, yes, friends. A lot of you are giving me the right answers. Good. Okay. So let me stop this